All right, happy Thursday. We have one problem left to do with calculus of vector valued functions. So let's go ahead and take a look. And we're going to evaluate this antiderivative, v cross the second derivative of v with respect to t. We're going to make an observation first. We look at this derivative. Using the product rule. Bless you. Wind up with dv dt cross dv dt, right? And then plus v cross second derivative of v with respect to t. This term right here, what is that? It's the zero vector, isn't it? Cross any vector with itself, and it's always zero. Of course, the zero vector is the additive identity. I don't know why I did dv dt. That should be d squared. We just get v cross the second derivative of v. So our antiderivative is really the antiderivative of the derivative of v cross dv dt, right? Well, there's a reason it's called the antiderivative. It's the opposite of a derivative. So if you take the antiderivative of a derivative, you just get the original function. Plus some constant vector. And there's our antiderivative. All right, so moving on. We're going to continue looking at some analytic geometry. A few things we're going to look at. We're going to look at arc length. Right, so you should recall from calculus 2, arc length is just the length of a curve, right? Well, now we're going to be able to find arc length of any parametric curve in space. We're also going to look at curvature, right? Broadly speaking, curvature is a measure of how much something curves. The larger the number, the more curve it has. And then 0 represents flat. We also look at 3 new vectors. One of them probably was already discussed in the video. The unit tangent vector, unit normal vector, and the binormal vector. Right, T and N allows us to create a new viewing window, so to speak, the Tn plane. Decompose every vector into its tangential component and its normal component. And then the binormal vector is just the vector that is perpendicular to both T and N. I think that's all we look at, right? Yes, it is. Starting with curvature. Curvature is a bit of a beast to calculate. Let's pull up my notes. I really need to hotkey these. So curvature by definition always hated drawing kappas. Kappa the magnitude of T prime of S. And so T is obviously unit tangent. So T prime be the derivative of the unit tangent. S is the arc length parameter. Right. Which is defined as a function of T. Specifically, it's the integral from A to T magnitude of R prime of UD, right? So it's just the arc length function. What you have to do once you find the arc length function is solve it for S. I'm sorry, solve it for T. So you want T as a function of S. Replace that function now in the actual parametric curve, you now have R of S. Then you have to find the unit tangent vector of R of S. Then you have to take its derivative and then take its magnitude. And that is curvature. It is a beast. Especially for those problems that you cannot solve for t explicitly. All right, what if you get an arc length function, let's say, of like sine of t plus t squared? Solve that for t. Not fun. Luckily, there are formulas that we can use to calculate. First, magnitude of t prime over magnitude of r prime. Notice this now eliminates the arc length parameter. That's nice. Right. However, that is still requiring us to find the unit tangent vector and then take its derivative, which again can be a beast. With some more simplification, we can show that's the magnitude of r prime cross r double prime divided by the magnitude of r prime cubed. This is the preferred method of calculating curvature, and it's the one that I will be using the most. However, there is another useful formula. What if the curve is given to us in the form y equals f of x? Then we can use this formula. Bless you. Absolute value of y double prime over the quantity of 1 plus y prime squared raised to the 3/2. We were given RT is t squared and 2/3 t cubed. First one, R prime. What's R prime? Then we want R double prime, which is what? Better. Now we need R prime cross R double prime. (8t minus 4t squared? No. That should be 8t squared, shouldn't it? Yes, it should. Then it's what, 0 minus 4t? And then you get 2 minus 0. You can factor out a 2 just to make life easy. We need its magnitude. So it'll be what? Absolute value square root 4t to the 4th plus 4t squared plus 1. That can be simplified. How do we simplify it?
E squared plus 1 squared.
Right, so that can be factored. Right. So if you take the square root of x squared, what's the result? Just do the square root of x squared. Right, be the absolute value of x, right? We don't need plus or minus here. Why? We don't need the absolute value.
If it's like curvatures, it has to be a positive value.
True. That's why we need an absolute value. Right. In this case, I'm saying we don't need the absolute value. It's not just because the t is being squared. It's also because you're adding 1, right? Right. 2t squared plus 1 will always be non-negative. Actually, always be positive. You'll never get 0 out of it either. And I'm going to just drop the absolute value. Magnitude of r prime. Oh, well, look at that. Isn't it the same? With the exception of the 2? So our kappa, our curvature, would be magnitude of r prime across r double prime over magnitude of r prime cubed. Simplify it. Two over the quantity, 2t squared plus 1 squared. Okay. And so here we're being asked to plot a curve first. Then we'll go ahead and find T, N, and D. What's the command? Do you remember? That would be if it was 2-dimensional. My parametric plot 3D. And remember, we need to now do the parameterization. It was 3 cosine, 3 sine, and 4t. And we need to specify a domain. I did minus 6 pi to 6 pi. Difficult to get this. It's a helix. Is it going to let me? Yes. All right. It's probably one of the best views. Unit tangent vector. How do we find it?
Do we take the derivative of R of t?
Just the derivative of r? So there's your unit tangent. Unit normal. How do we find the unit normal? Then we have the binormal B. It's just t cross n. So what is r prime?
Three negative three sine t. 3 cosine t. And 4.
Right? We now need its magnitude. Magnitude should be easy. Magnitude is 5. There are t. Is 1/5 r prime. I'm just going to distribute that 1/5 through. We now need its derivative.
It's sine t. 0.
Magnitude. Again, should be very simple to find. Just 3/5. Our normal vector. 5/3. Times our t. And then just distribute the 5/3 through. Binormal is our unit tangent. Frost, our unit normal. And factor out a 1/5. Not necessarily to factor out that 1/5. I just don't feel like working with fractions in the cross product. First component would be what? -4 sine of t, right? 0 minus 4 sine t. Second component would be -4 cosine plus 3 sine squared. Oh, no, I looked at the wrong one. It'd be -4 cosine minus 0.
Sign negative or not? Wrote it twice, I think.
That sign is negative. Which would then make this positive here, right? I don't think I had the negative when I did that. Nine sine squared minus -9 cosine squared. Oh, why am I doing 3 times 3? I have no idea what I'm seeing. It's a Thursday. It's not even Monday. And I'm just going to distribute that 1/5 back through. That, of course, is just 3. That would be the binomial vector at any point t. Right, so finding length of a curve. This is an extension from Calculus 2. Right, at the very end, you looked at arc length of parametric curves. Right, and it was the integral from a to b of the square root of the derivative of the x component squared, right? Plus the derivative of the y component squared. In space, add that additional z component, but that is precisely the magnitude of the derivative of the vector, right? So same formula, we're just simplifying it. We need r prime. Oh, this is easy. 5, 4, 1. Means its magnitude. (25) plus 16. 41. And then plus 1 would be 42. 42 is 6 by 7. Right, so prime factorization 2 by 3 by 7. So that can't be simplified. Arc length is the integral from 2 to 3, root 42 dt. Which is just square root of 42. So there's your arc length.
Though, because the difference was 1, right?
That and because it's a constant that we're integrating. Right, so it's root 42 times the length of that interval, which happens to be 1, right? If say 2 to 8, it'd be 6 times root 42. All right. Okay, there's another arc length. And so we're given this curve, we want to compute the arc length function. Notice we just want the function. And we're not asked for the parameterization. If it doesn't give you an interval, just assume that the interval starts at 0. So we're going to integrate 0 to t. Magnitude, oh, I don't want t because I'm using 0 to t. So magnitude of r prime of u du, right? They don't like it, right? If I would have kept it as r prime of t dt and it goes 0 to t, they don't like that. Even though it's the same bloody thing. This means we need to find r prime. That is going to require two product rules. It's also going to require what? 5 chain rules? Chain rules aren't too bad. The 4 product rules, that's fine. But at least this isn't a terrible function to deal with. Forgot the bloody 2. That should be the derivative of the first component. There's the second component. And then there's the third component. We get to take its magnitude now. Oh, this will be fun. First component squared. Right there. Right? Second component squared. And then that final component. So since I did on multiple lines, here's how I'm going to write it. And so it's understood that's the square of that entire thing. Oh boy, that looks hideous.
Is that like a mathematical thing, or is it just common, like, math, like just like a thing? Yeah, that's what-
Yeah, it's kind of a combination of math, shorthand, and coding. All right, so a lot of time if you look at coding, it doesn't do an entire square root, right? This will be the symbol. And it would just look awkward if I just put the line over that first term, right? And then it's like, well, am I really taking the square root of the whole thing? Look how sexy that is. The two red will simplify to 25e to the negative 10t. The two orange simplify to 0. The two yellow simplify to 4e to the negative 10t.
Like which one, like each of them, like. Result to the red one, orange on the yellow one, sorry, this. Gentleman.
Right, so the reds are the 25e to the minus 10t. The yellows are the 4e to the minus 10t, right? And the oranges cancel out, so it's 0. Although, why didn't it count that crossing of t? For Pete's sake. Yep. And that just simplifies to what? Square root of 54e to the minus 10t, right? 54. 6 by 9. So I'll simplify to 3e to the minus 5t root 6. So that hideous looking magnitude turned out to be something very simple. Right, which becomes a very simple integral to evaluate, right? And so there's the arc length function. If we wanted the arc length parameterization, we would then have to solve that for t, which in this case isn't actually too terrible, is it? We would have what? That would be t. And they have to plug, you have to go back to what RT is and replace t with this function, with that expression. And that would be your arc length parameterization R of S. Right, so it would look hideous. But it's actually not too terrible. Until I then say, okay, use the definition to find curvature, right? You have to find the unit tangent vector of R of S and then take its derivative and then take its magnitude. And with all this, that's going to be very hairy. Any questions so far?
Through a little bit, is the bicentennial 3 rather than 6, 5 negative for the first one? Like, when you plug in, you reconsider.
Because I switched the order. Right, so I can get rid of the negative by flipping this order. Right, so do it the right way, right, and you get negative and then minus negative, which would be positive. Anything else? So there's still one problem left for this, but we don't need it for the quiz. So the quiz is going to be a little bit different. I forgot to print out the quiz. Oops, that's number 7. That's not the one I want. That's what I want. So just do this on loose leaf paper, and then you'll turn that in instead. If you don't have loose leaf paper, I happen to have some with me.